Hi, I'm now in the last lecture for this particular series, and I'm going to cover hashing. I took a different route when I looked at hashing. Instead of I looked at professors' lectures and I looked at some other material, but I really wanted to understand. There were some questions that I had, and I always kind of had some questions about hashing, which I wasn't able to answer or get an answer to. So I looked for some more material, and what I really found is there are at least two sets of lectures by Professor. If you have the CLR book, the Introduction book to Algorithm book by Professor by Professor Charles himself, and those are really very good lectures. So I would definitely encourage everybody who really wants to understand this to look at lecture 7 and lecture 8 of Introduction to Algorithms and just search for this particular text. Just search for Introduction to Algorithm by MIT Open Courseware, and you will get these two lectures and just go over them in detail. That is very explanatory. Each lecture is about an hour and a half, so I'm trying to do justice to those to that content in about 10 or 12 minutes. So I'll definitely be very brief, but I would definitely encourage everybody to do that. And if you can't look at the 7th lecture, just at least look at the 8th lecture. That I think is good enough. Okay, so hashing, everybody understands hash table. The idea is a direct, an order one, order one, get. That's the basic idea. And how do you do this? You can imagine, you can imagine is, in everything is order one. Okay, you can imagine is that you have a function, you have an array, and you have a function. The moment you get a key, you get directly map some. You directly map that key to a particular element in that array, right? If you do that, and if there isn't any already an element in that array, it means it's order one. So the range of keys can be large. For example, in this case of 64-bit numbers, there are lots and lots of keys, and character strings can be even larger, and you obviously cannot have an array of that high size. So what it means is you have to deal with collisions, and you don't want to just really allocate an array of, let's say, even if you have a very large array, let's not worry about the 64-bit, but you don't want to just have a large array with a lot of unallocated spaces. Maybe if you have a very simple case where you have a very known case, but you don't really care about memory and you're optimizing for something else, then maybe that's the case. But you don't want to do that because there are better schemes to address a perfect hash. Okay, so in the naive case, that there are, just looking at the pigeonhole principle, there are a lot more keys that go into buckets. So you'll have some, you'll have at least, you will have more, you'll have one, or you will have two or more keys going into the same bucket. And what it means is there is a collision, and you have to deal with collisions. So there's two strategies. There are probably multiple strategies, but there are two strategies at least that they talk about in the lecture and in the books. The first is the linked list way, that given a particular element, you kind of do this. You have attached a linked list of all the other elements or that also hash to the same bucket. And once again, the worst case is if everything hashes to the same slot and it's order n. But hopefully that is not the case if you have if you choose a good hash function, and we'll talk about that. And okay, so this is just some load factor. Just remember, this load factor is the number of keys per slot, right? Which is n times n, where n is the number of keys and n is the number of slots. So that's the load factor. Typically, you would want this to be 1. If it is 1, it means that, well, no, it's okay. If it is 1, it means that ideally there should be 1 key per slot, but that doesn't mean it is 1 key per slot. Okay, so that's the load factor. And the expected time for an unsuccessful search is 1 plus alpha, right? That's because alpha can be the, let's say if it is 2, it means that you have to look, let's say if the load factor is 2, it means that twice the number of keys, the number of slots, and if each of them is uniformly distributed, it means that you will have to go to the key and then look at the linked list in that particular bucket. So that is alpha. But once again, that is the ideal case. How do you choose a good hash function? Once again, what it should try to achieve is distribute keys uniformly and regularity in key distribution should not affect this uniformity. What that means is there will be some distribution in keys itself, and that should not affect the way you are trying to distribute them. Typically what people do is they try to do a modulus. This is very important. Don't pick an M that has a small divisor D. A proponent, what it means is that if you put 16 or something like that, 2 raised to 4, then it's only going to look at these these significant digits in any given number, right? So you do not want to do something like that. And if M is, for example, here, if M is equal to 2 extreme, this is called extreme deficiency. If M is equal to 2 raised to R, then the hash doesn't even depend on all the bits of K. For example, if R is 6, then hash just depends on these last 6 digits of the key of K, which is very, very bad, right? I hope you just think about it, right? So let's say, for example, if it is 2, then the only thing it depends on is whether the number is odd or even, right? It only depends on this guy, right? 2 0 to 0 to 0. If it is 4, it only depends on this thing, which is very, very bad. So that's the idea. So don't do that. And typically what we do is we pick M to be a prime, not too close to be a power of 2 or 10, and not otherwise used prominently and in the computing environment. So it's sometimes a little bit inconvenient, but it's a little bit proper. It's popular, and that study is done that when you choose a prime number, it really helps. And we will, but there are other methods as well. Although the next, okay, so so another way, instead of just using the modulo M where M is prime, another way to do is just read about this. I'm kind of going to skip this because I'm actually going to go over the right, the way it's actually done, which I think is more interesting anyways. So it's the multiplication method where you can do all sorts of interesting things. So just look at it. The idea is you get A times K mod 2 raised to W. R is such as this right shift, W minus R, where the computer has W by 2 words, and you can do something like this to figure out the key. And you can see why that is interesting. Okay, so there are two things I think we just want to cover before we go here. Instead of one is linked list. The other thing, what you can, instead of just doing a linked list based thing, you can also do something called as open addressing. What that means is if you have another secondary hash function, where what that means is if there's already a collision here, then you apply the secondary hash function, and you kind of say, oh, okay, there's already a collision here, so let me put it there. So that's the idea here, and and so on and so forth. So the search uses the same sequence, terminated successfully until you find the keys and successfully, right? So that's the basic idea here. So you use all these keys, just you don't want to, okay. And that is called as linear probing. Okay, so but let me talk about what really works. So this is what really works. Okay, universal hashing. The idea is you can always figure out, given any hash function, you can always figure out an extreme case whereby the degenerate case whereby everything is order n, correct? Everything hashes to the same bucket, or and whatever you try to do, all the other elements, whether you do even this multi-order, probing, they all eventually end up at the same place. So you can always figure that out. And the idea is that since there are more, there are a lot more keys than the number of buckets you have, there will be more than there will be some large number of n keys that will that will fall into the same bucket, and if you create a test by just picking those n keys, they will then all land in the same bucket, and that will kind of break your hash. The thing that we can always do is the idea of universal hashing is that you pick a hash function at random, independently of the keys. What it means is there is no fixed hash function. Every time you're picking a different hash function, and then even if somebody looks at the code, they can still never figure out at runtime what hash function you're going to use. So they will never be able to, on average, break it that easily. And the interesting thing about is about universal hashing is how do you figure out, how do you construct this kind of hash, this set of hash functions. So I've already spoke about this. H is universal if for all x, y element of u, where x is not element of y, we have a function, we have h, which is element of h, given any function h, and h, x is equal to hy is this probability, right? So what does this mean? That given a function, given a random function h in h, such that the probability that hx is equal to hy, that both of them go into the same bucket, is the number of functions in h, the magnitude, that is the number of functions h, divided by m, where m is the number of buckets. Okay, so just think about it. What you're saying is that let's say if you have just one, function. In this case, the probability that hx is equal to hy will be 1 by m, because the modulus of h is 1. Okay, so I might have not explained that well, so let me try it again. So the idea is, what does this statement mean? For all keys x and y, for all keys x and y element of u, which is the universe of keys, where x not equal to y, the number of functions where hx is equal to hy, what that means is both x and y map to the same bucket, is the total number of hash function divided by m. Okay, what does that mean is, let's say if this is h is the total set of all functions, then there is a very small set of these functions and what is the the fraction of this set? It's 1 by m of the total h, where both x and y will map to the same bucket. What that means is that if you pick any function at random in h, what is the probability that x and y will be in the same bucket? It is 1 by m. Does that make sense? So that is kind of the key idea, that they collide is 1 by m. And if that happens, that's golden, right? That's what you want to do. You want to the collision that x and y, the probability that x and y will be should collide will be 1 by m, because they can. What that means is that both of them map to the same bucket, that is bucket 1, whereby there are m such buckets. So this is ideal, right? So that's what you want. This is universal hashing. So how, what does that? So let's see the proof of this. First is, this is just trying to prove that the expected value is a. So I think we understand this, correct? So does everybody? I hope everybody understands this. That given the definition of universal hashing, it kind of follows from the definition that given any elements x and y, they will, the probability that they collide is 1 by m. It just follows from the definition, and. The theorem, so once again, let's look at it. Suppose, let's pick a function h at random. H is used to, hash n arbitrary keys into m slots. Thus, for any given key x, we have e, the number of collisions with x is less than n by m. Okay, the number of collisions for any key, it is less than n by m, where n once again is the total number of total number of keys that you pick. And let Cx will be the random variable denoting the total number of collisions of keys in T with x. And what that means is it's 0 if xx is equal to hy, and sorry, 1 if the hash values are the same, and 0 otherwise. Now note that E expected of Cxy is 1 by m. This is by definition, and hence expected of C of x is summation of all Cxy, where y ranges from for all other elements minus x, where x is the same element. And so it's expected of C of x is expected of this thing, and you kind of do some algebra linearity, and it is expected of 1 by m. So just the expected value of the collisions in x is n minus 1 over m. And that's kind of what you want, right? That is ideal. This is the load factor. So it just, once again, it's kind of obvious, but this is just by definition. Now, the important thing is, how do you construct a universal hash function? Okay, So I shouldn't rush. Let me make sure everybody understands this, right? So once again, what you're trying to figure out is expected number of collisions of different members with X, and you reach to the conclusion that it is equal to the number of elements or number of keys divided by M, which is ideal, right? That's what will happen. So that's, it boils down to that. And once again, we kind of started. That's what you want to, you want to prove, right? It's less than n by 8. Well, we know this, and we basically figure out, okay, what does this mean? It's equal to, n minus 1 by m. So just so that we are not confused, this is number of collisions with X, right? So kind of the same thing. Okay. So now, how do you construct a universal, construct such type of universal hash functions? This is a particular strategy. This is a particular strategy that let M be prime. Now this proof is important, so just go over the proof with me. Let M be prime. Decompose key k into r plus 1 digits, each with value of the set 0 to m minus 1. Okay, so you're kind of dividing this key by m every time, so that this k is equal to k0 into m raised to 0 plus k1 into m raised to 1. You get the idea, plus kr into m minus 1. Once again, so you do this. Now you pick a particular set A from A0 to AR, where AI is chosen randomly from 0 to m minus 1, and you define h of k given that particular vector A as the summation of AI times ki, okay, A0 times K0 modulo m, and then you do this summation, and you do this across 0 to r. Okay, you do this across 0 to r. So once again, why this will be fine? Because as you can see, any such number modulo m will be a number less than m. It will never be a number greater than m. And you add all these things, and they will. So think about it. Where will they lie? What will be the summation of this? So So it will be dot product. Sorry, it will be this entire thing modulo m. Okay, sorry. So it will be this dot product of all these. First you take the dot product, take the sum, and then you modulo m. So it will always fall between 0 to m. Now, and how big is h? H, which is equal to h of a, it is actually this particular, m raised to r plus 1. Why? Because how are you forming this particular set A? You're forming with any such, A can take any values between 0 and m. A1 can take any values between 0 and m, and so on and so forth. So this entire vector A can take any values between can take m times m so as to r plus 1. So it can take m raised to r plus 1 values, correct? So you look at this vector A, because this is what is random, correct? This is fixed for a particular key. This is what is random, and since you're picking this at random, what it means, you're not doing it for every key. It's not random. Not for every key it's random. You pick. You have this entire set of functions, and you randomly pick a function from this entire set. So it's m raised to r plus 1, and now you have to prove that this is universal, and this is I would like you to let's actually go over this proof. It's actually a very interesting proof. So let's say you suppose x0 is this and y0 is this, be distinct keys. Thus they differ. So since they are distinct, they differ in at least one digit position. Let's assume it is x0. This is just the without any loss of generality. That's what this means. Without any loss of generality, it's position 0. It just keeps the math easy. And now you have to figure out how many there are how many such functions where x and y collide, right? And you want to prove this is 1 by m. That's what you want to prove. So you want to do this, which implies that this is true, correct? Modulo m. This is just by definition of how you created the functions. what that means is now you're subtracting both sides by this, and then once you do this, you kind of take this out and plus this, and what it means is this is equal to this modulo m. Once again, this modulo m is kind of stays there, and okay. So once again, so I hope so this is still clear, right? Yes. And in this case, what we are saying is that they differ by at least one position, and we are assuming that position is x0. That x0 and y0 are not the same, because they since they are distinct, they should at least differ by one. So you do this, you take this to the right side, and now from number theory, this is important. Let m be prime for any number z, a part of z of m, such that z not equal to 0. There exists a unique number z prime such that z times z prime is equal to 1, modulo m. What that means is, look at this number 1. 1 times 1 is modulo 7. Modulo if m is 7, it's the z prime is 1. If it is 2, the number should be 4, because 2 times 4 is 8, modulo 7 is again 1, and so on and so forth. One thing interesting, you see that this is kind of transitive or reflexive, because 2 2 and 4 4, 3 3 5 5, etc. That kind of shows up. So you know this by number theory. And now coming back to the proof, this is where we were, and since we know that this is not equal to this, an inverse of this must exist, correct? Because we know that this number is not 0. And what you're now doing is you are kind of multiplying both sides by that inverse. And the moment you multiply that by the inverse modulo m, this is simply a0. And thus, this is important, thus for any choices a1, this ai, right? a1 to ar, exactly one choice of a0 causes x and y to collide, correct? What that means is once you fix ai, a1, a2, etc., there is only one a0 that so you can't now you can't change a0. You cannot change a0 from 0 to m, that you could, is m minus 1, that you could. What that means is that this is that a0 is fixed, and what that means is the total number of hash function that can exist is is a. Since a0 is fixed, it means it takes one value and everything else can vary, which is m raised to r. So the total fractions of number of functions of h is m raised to r divided by m raised to r plus 1, which is 1 by m, and that's what you need, right? So so this is just now this is just stating that what we already, so m choices, but once of this already shows exactly one choice for a0, namely this, the number of functions is m raised to this into 1, which is m raised to r, which is exactly h times n, right? Because h was m raised to r plus 1 times n, hence proved that this is a set of universal hash functions. So this is very interesting, isn't it? I was actually very happy when I learned that, okay, I can actually go this proof by myself. Now let's look at perfect hashing. The idea here is that there are two-level scheme, that in case if you hit a particular, if multiple buckets, if multiple keys do hash into the same bucket, there is still it will still take order 1. What that means is that you can figure out another hash function such that you can immediately get to it, and that there will be no such collision here, and no collisions at level 2. Okay, so that's kind of the idea, that's the proof. And here 4 is the length of the array length that is maintained, and in this case it is 1, and 9 is and this is always half full. Okay, so that's the idea. So you see there is some wastage here, but it's not a lot. And so this is the proof here, and this is the proof, and this is what you want to prove. I'm just going to let's try going over this proof as well quickly. Let me see whether I have enough time. Okay, so in the interest of time, I'm going to skip this proof. This lecture is already 25 minutes. Although once again, I'm trying to compress 2.5 hours worth of lecture into 25 minutes. So still, I would hope it is helpful. But then I don't want to drag this to a 45-minute lecture. So take a look at these slides. They are actually once again very probabilistic. There's this Markov's inequality. You need to know that to complete this proof, that for any non-negative random number x, we have probability of x greater than or equal to t is less than equal to expected value of x divided by t, and you can kind of get this thing to done. And the other thing is that the total number of slots that you use, because you see that you're kind of using the square value of this. Even if you do the total number of slots, and if you figure out the expectancy of this number, right, where ni is the ni be the random variable for the number of keys that hash into slot I in T, where T is the hash table, and so what is the probability that that there are no collisions, there's one collision, then two collisions, and things like that. And if you do that, you will see that the expected value of this is still order of n, and this is looks like this. I probably missed this, and I should go back and check. It's using bucket sort. So once again, when you have a random set of keys and you're kind of doing these buckets, it's still order of n. It's not order of n square or something like that it may appear to be. So that's kind of the basic idea here. I hope I hope this answered a lot of questions about hashing and universal hashing and perfect hashing. There's also, I do want to say something more. There's also something called as minimal perfect hashing here. And what it means, minimal perfect hashing, and what it means is if you already have a set of keys that are known, how can you then construct a hash table for this set of keys, which is minimal in storage and obviously perfect. This is beyond the scope. I'm still reading that up, and hopefully I can add another video for just minimal perfect hashing sometime later in the future. Okay, thanks, bye.